Graphs are the natural way of modelling relationships between objects, from molecules to social networks. They are ubiquitous in our daily lives. When we ask for directions to our map application, it's using a shortest path algorithm over a graph to answer us. So it may then come as a surprise to find that the very natural question, are these two graphs equivalent, has yet to come to any conclusive answer and is still a very active area of research even to this day. The question is formally known as the graph isomorphism problem, and its applications range from chemistry to computer vision. On the more theoretical side, the problem is of central interest in areas such as logic, algorithmic group theory, and quantum computing. It gained prominence in the 70s when it emerged as one of the few natural problems in NP that could neither be classified as being NP-complete nor shown to be solvable in polynomial time. Determining the precise computational complexity of graph isomorphism is regarded as a major open problem in theoretical computer science. It was realized that graph isomorphism has aspects that distinguish it from most NP-complete problems, as counting the number of isomorphisms between two graphs is not harder than deciding whether or not there is an isomorphism. In other words, checking the solution is not harder than finding the solution. Moreover, it was shown that the complement of graph isomorphism has short zero-knowledge proofs, another indication that graph isomorphism is not NP-complete. In order to understand such results, let's clearly define the problem. Three important concepts are isomorphisms, automorphisms, and canonical forms. An isomorphic form from a graph G to a graph H is a bijection π from the vertices V onto the vertices W that preserves adjacency and non-adjacency. That is, UV belongs to E, if and only if πu, πv belongs to F for all pairs UV within V. An automorphism of a graph G is an isomorphism from G to G itself. For example, all n factorial permutations of the same vertex set of a complete graph Kn on n vertices are all automorphisms. The collection of all automorphisms of G forms a permutation group, which demonstrates that automorphism groups can get very large. But fortunately, every permutation group has a generating set linear in the size of the permutation domain. The problem of deciding whether two graphs are isomorphic and the problem of computing a generating set for the automorphism group of a graph have the same computational complexity, so they can be reduced to each other by polynomial time reductions. A canonical form gamma maps each graph G to an isomorphic graph gamma G in such a way that if graphs G and H are isomorphic, then the graphs gamma G and gamma H are identical. This yields an isomorphism test. Given two graphs G and H, compute gamma G and gamma H and check if they are identical, which can be done in linear time. In practical applications, canonical forms are often preferable over isomorphism tests. In the aforementioned case of molecule matching, it is more practical to compute the molecule's canonical form and store it in a database, as a way to avoid repeating the computationally expensive step. There are two approaches to solving the graph isomorphism problem: combinatorial algorithms and group theoric algorithms. We'll talk about both. Firstly, combinatorial algorithms try to find a certificate of non-isomorphism, focusing instead on proving that graphs are non-isomorphic rather than trying to find an isomorphism. For example, if the number of vertices, edges, and triangles in both graphs are not equal, then the graphs are non-isomorphic. Of course, if they are equal, it doesn't mean that they are necessarily isomorphic, hence we need a systematic approach to generate such certificates. The Weisfehler-Lehmann algorithm provides a systematic approach to generate them in an efficient way. Actually, it's a whole family of algorithms parameterized by a positive integer called the dimension. The one-dimensional version is known as color refinement. It's one of the most basic ideas in graph isomorphism testing, having been reinvented multiple times. It iteratively computes a coloring of the vertices of a graph, with the final coloring having the property that any two vertices of the same color have the same number of neighbors in each color class. As detailed here, you can see the process of color refinement only requires a simple initialization, one repeated refinement step, and by the end of the process you will have a stable coloring of the graph. This coloring is an isomorphism invariant, meaning that two isomorphic graphs have the same number of nodes of each color. Thus, if we were to run the algorithm in two graphs and they were colored differently, we would know with certainty that they are non-isomorphic, and that the algorithm distinguishes the two graphs. Note, however, that the reverse is not necessarily true, so if two graphs do have the same colors, that does not guarantee that they are isomorphic. But remarkably, color refinement does distinguish almost all graphs in a precise probabilistic sense, since it is able to distinguish a great deal of all possible graphs on n vertices. This algorithm is very similar to the standard algorithm for minimizing deterministic finite automata. Borrowing ideas from Hopcraft's DFA minimization algorithm, color refinement can be implemented to run in time O n plus m times log n, where n is the number of vertices and m is the number of edges. As mentioned before, color refinement is not a complete isomorphism test, since it fails to distinguish simple non-isomorphic graphs, as seen here. The k-dimensional Weisweiler-Lehmann is based on the same iterative refinement idea. However, instead of vertices, KWL colors k tuples of vertices in a graph. Initially, each tuple is colored by the isomorphism type of the subgraph it induces. Then, in the refinement rounds, the color information is propagated between adjacent tuples that only differ in one coordinate. This algorithm is more powerful, in the sense that the pairs of graphs that are distinguished by the k-dimensional Weisweiler-Lehmann algorithm form a superset of the ones that are distinguished by the k-1 dimensional algorithm. It's highly non-trivial to find non-isomorphic graphs that are not distinguished by 3WL. However, for every dimension k, there are non-isomorphic graphs that are not distinguished by KWL. These graphs are known as CFI graphs. They have size big OK, and are 3 regular, meaning that each vertex has 3 neighbours. There are many graph classes that do not admit CFI graphs, in which case a low-dimensional WL is a complete isomorphism test. This includes the class of planar graphs for which 3WL suffices. On the group theoretic approach, Lux developed a polynomial time isomorphism test for graphs of bounded degree. That is, if we were to fix the maximum numbers of neighbours a vertex can have, the algorithm time would be polynomial. This is done by solving the automorphism group of a graph problem, since they are polynomially equivalent. To understand the algorithm, some permutation group concepts are required. To briefly run them down, a permutation domain includes the objects that are permuted, a symmetric group is all permutations, an alternating group is even permutations, that is, products of an even number of transpositions. The giants are both of those groups. Orbits are equivalent classes of objects that can be mapped to one another. Transitive group is every object that can be mapped to every other object. A block is a subset of the objects that is always mapped back to itself or somewhere else entirely, and a primitive group is a permutation group whose blocks are singletons, or the entire permutation domain. Starting with a suitable group of permutations, we want to compute within it the automorphism group A of interest. This is done by continually maintaining an encasing group gamma greater than or equal to A, containing all automorphisms as a subgroup. Then, gamma is iteratively shrunk until it agrees with A. If the group only has one orbit, we exploit blocks whenever they exist. The set of images of the block partitions the domain omega into blocks of equal size, which together form a block system. The group gamma permeates the blocks of the system, and we can consider the induced permutation group complement gamma on the blocks. By choosing B as a subset of omega, inclusion-wise maximal along the blocks, we can ensure that gamma complement doesn't have any blocks itself, meaning it's a primitive group. In polynomial time, we can reduce the computation of the automorphism group A to mod complement gamma computations, each involving subproblems with significantly smaller orbits, which can then be processed as mentioned above. In the case the group is already primitive, we use a brute force algorithm inspecting all permutations in gamma. The bottleneck in this algorithm arises when complement gamma is large, constituting what is known as a Cameron group. In that case, complement gamma is a large primitive group, and the only recourse is to brute force the permutations. Or it was the only recourse, until Babai attacked exactly this bottleneck, improving the running time of the theoretically fastest general graph isomorphism algorithm. Babai proved that graph isomorphism is in fact solvable in quasi-polynomial time. This means that on an n-vertex input graph, Babai's algorithm runs in n to the power of p log n time for some polynomial px. This can be interpreted as the problem being almost efficiently solvable theoretically. The general strategy of the algorithm is to reduce a problem instance to quasi-polynomially many instances that are all smaller than the original instance by at least a constant factor. This is continued until the recursive instances are sufficiently small to be resolved with brute force, leading to an overall quasi-polynomial time algorithm. The detailed explanation of Babai's algorithm required non-trivial group theory, as so it is beyond the scope of this presentation, as in practice it is excessive to even run the two-dimensional Weisweiler-Lehmann algorithm, let alone some version of increasing dimension as in Babai's algorithm. Current practical isomorphism test packages rather use color refinement, which, as mentioned, is already sufficient enough for most graphs. If it turns out not to be sufficient, then the algorithm can take the route of branching by using the concept of individualization. Specifically, it assigns one by one a different colour to all the vertices in a colour class. This breaks the symmetry, and subsequently colour refinement could be potentially applied again to produce a more refined partition of the vertices. In a backtracking manner, this continues until a discrete colour has been reached. We've explored the different methods for performing graph isomorphism. In practice, it is used to find symmetries of combinatorial objects, and as such they have numerous applications in miscellaneous domains. In the context of optimization, for example, in SAT solving, symmetries are exploited to collapse the search space, as parts equivalent onto symmetries only need to be explored once. Other application domains include machine learning, computer graphics, software verification and model checking, and mathematical programming. Hopefully this video has given some context on why graph isomorphism is such an important problem to tackle, and given some more insights on the techniques and strategies used to try and solve this problem as efficiently as possible.